Welcome back to the PACAT Chemistry Review, and we will be talking about chemical bonding, molecular geometry, all through the lens of VSEPR theory. Following OpenStack 2nd edition, as usual. So let's talk a little bit about covalent bonding first. So this is something that happens with nonmetals because they tend to share electrons with each other, and that is really the definition of covalent bonds when we have electron sharing. So considering the simplest molecule out there, hydrogen, H2. So over here on the left, if we look at a hydrogen atom, it has one electron, one proton. So when you create the H2 molecule, because they are each contributing one electron and they're sharing them between the two, then effectively the net result is each hydrogen has a 1s2 electron configuration. Or in other words, they have the same configuration as helium, which is a noble gas, which is quite stable. And so this stability has been attained by sharing. So in terms of the covalent bond, so sharing is always going to happen, but you can have a situation where you have equal sharing of electrons. So this is what we call nonpolar covalent bonds. Or if there's unequal sharing of the electrons in the covalent bond, then it is polar. And this polarity difference all has to do with the electronegativity difference between the two bonded atoms. So that begs the question, what is electronegativity? So electronegativity, this is something that is inherent to different atoms, to different elements, and it's a measurement of how well they attract electrons towards themselves when they are in a chemical bond. So this is something Linus Pauling came up with, and it was then realized that there is a definite trend in electronegativity on the periodic table. And these increases and decreases are listed here in words, but I really like to show the periodic table itself. And you can see that arrow along the top, increasing electronegativity. It goes from the left over to the right. And this goes along with this concept of effective nuclear charge, where as you go across a period, you see an increase in effective nuclear charge, and that is essentially how strongly the electrons are feeling the nucleus. So it ends up that fluorine is the most electronegative atom. The numbers that are listed below each of these elements, that's the electronegativity value. So fluorine is at the top of the scale. The largest electronegativity there is 4. And then going down a group, it decreases. That electronegativity gets smaller and smaller. And so francium, that's Fr, that element on the lower left, that will have the smallest electronegativity. That will have the smallest ability to be able to attract electrons towards itself, as opposed to fluorine that is pulling electrons very strongly towards itself. Okay, so this question here, just throwing that out there, that the noble gases are not listed on this periodic table, and that has to do with the fact that electronegativity is a measurement of how well an element pulls electrons towards itself in a bond. Well, noble gases really rarely bond to anything, and so talking about their electronegativity isn't done very much. All right, so let's look at those pure covalent bonds. Those are the ones where we have two atoms bonded together and it's a pretty equal sharing of electrons. So this is of course going to happen whenever we have two elements that are the same. They're going to have the same electronegativity. They're going to share equally. That can also happen if you're looking at the overall molecule and it's symmetrical so that polar bonds cancel each other out. We'll see examples of that later once we start looking at molecular geometry. And because carbon-hydrogen bonds are so common in all of organic chemistry, then it is worth saying that carbon and hydrogen have very similar electronegativities. And as a result, those CH bonds are considered pure covalent bonds where they have equal sharing of electrons. Polar covalent bonds, on the other hand. So we've got elements bonded together that have significantly different electronegativity values. So we see this very often. Of course, whenever something's bonded to fluorine, that's going to happen. Oxygen's another electronegative atom. And so you end up seeing this polarity difference whenever you've got significant differences in electronegativity. And as a result, we can use this notation here. This is a lowercase delta. And delta positive means that there's a partial positive charge, whereas delta negative is partially negative. That's negative side's going to be on the side, on the end, with the more electronegative atom. So here's an example. If we've got HCl, hydrogen and chlorine bonded together, it turns out that chlorine is more electronegative. So indeed, they are sharing these electrons. Here, these dot structures are showing how many valence electrons that chlorine has. Chlorine is in group 7. It has 7 valence electrons. Hydrogen is in group 1, having 1 valence electron. So bringing these together, then this is where they are sharing those two electrons, a pair of electrons. That means we have a single bond. These over here, these other pairs that are around the chlorine, these are called lone pairs. These completely belong to the chlorine. We can also indicate a single bond by drawing a line. So this line here means that there are 2 electrons. Very common notation. So in terms of this idea of polarity, because the chlorine is more negative, we can show it this way, where there is an arrow, this notation here, an arrow points towards the more electronegative atom. And this crosshatch here, this is used to indicate the element, it's on the end with the element that is less electronegative. So it's going to be a partial positive. And you can see that that crosshatch right here, it shows at the end of the arrow that we have kind of something that looks sort of like a plus sign. There's another notation that's shown over here on the right, and that is showing that delta positive, delta negative. Same idea. This is one notation, and this arrow, this vector model, is another. But they both show that this is a polar molecule, and this is a polar bond between the hydrogen and the chlorine. So electronegativity does influence the bond type. And so this column here is showing the electronegativity difference between the bonding atoms. So if they have the same electronegativity, we talked about this before, pure covalent bond, there will be completely equal sharing of electrons between the 2 atoms. Somewhere in between. This is what we saw with the hydrogen and the chlorine. So we have somewhat difference in electronegativity, and that's where we get a polar covalent bond. Now, if we do have a really large difference in electronegativity, the net result is pretty much that the electron has been lost from one of the elements and gone completely over to the other. And then we have 2 charged species. So that would be like a sodium +1 and a chloride -1. And that is an ionic bond. We're not talking about ionic bonds right now, but I just wanted to show how that fits into the whole picture. All right, so in order to understand the structure of molecules, we need to start out with this idea of Lewis structures. So this is essentially a bookkeeping method. This is where we are looking at the valence electrons on all the atoms that are involved, and we're seeing where they are. Are they being shared between 2 elements? Are they lone pairs like we saw with the chlorine in the previous example? So this is figuring out where the bonds are and where all the electrons are. Now, we usually just see this with main group elements. That's because main group elements are where the nonmetals are. Nonmetals undergo covalent bonding. So what we need to do here is when we are drawing out the Lewis structure for a molecule or for a polyatomic ion, these valence electrons occur in pairs. And so they're going to be, if they're shared between the two, then there's our covalent bond. I showed a picture of that earlier. We can draw that as a straight line. And then those pair of electrons, those lone pairs, we show those as dots normally in the final structure. Another thing I wanted to point out is the octet rule. This is something that you can follow most of the time, and I'll point out those important exceptions to this. So nonmetals, generally speaking, they are most stable if they have 8 electrons, and in other words, they are isoelectronic. They have the same number of electrons as noble gases, which are very stable. They have all of their orbitals filled in a shell, very stable situation. So hydrogen, this is a common octet rule because hydrogen is so common in so many molecules. It can only hold a duet or 2 electrons in the 1s orbitals. Then it's full and then it is stable. And there are some other exceptions we'll mention. Boron, for example, is fine with 6 electrons. And then we have some of the larger nonmetals can hold up to 10 and 12 electrons. So some examples of Lewis structures. Here we have ammonium. So this is showing with these lines, we have a pair of electrons, pair of electrons, pair of electrons here. And also I wanted to point out, if we have a polyatomic ion, then using the brackets with the charge on the outside is our notation of what the whole charge is on that polyatomic. We see that here as well with the hydroxide ion. There's our negative charge. And here we can see an example of a single bond, and we've got our 3 lone pairs. And here's another example of a Lewis dot structure. This is of water. Water has 2 lone pairs and 2 bonds. Now here you see these bonds are shown a little bit bent. And in terms of Lewis dots, you don't need to worry about bond angles. We're really just counting up the electrons, making sure we're all there. But we will worry about bond angles as we begin to talk about molecular geometry. So some more possibilities here. Here's a double bond. So when you see double lines, double bond means that there are 4 electrons present. There is essentially 2 electrons per line, since each one of these lines means that there's a bond. So ethylene on the left, we've got a double bond. And then acetylene on the right, that is a triple bond that shows those 3 lines that occur between the 2 carbon atoms. So in writing Lewis structures, okay, the very first thing we need to do, we need to figure out how many total valence electrons there are in the whole molecule. Unless we're dealing with, if this is a polyatomic, and then we need to make sure that we do take care of the fact that the polyatomic cation has 1 less electron overall. So we would have to delete that from our total count. And for anions, we count up the valence electrons on all the atoms present, and then we would add an electron for each charge that anion is. Okay, so once we've added up all of the electrons in the molecule, then that's when we would want to draw a skeleton structure of this molecule. So we figure out what the central atom is, and then we put the other atoms around it. We draw single bonds to them first, and then we figure out how the octet is going to work out. So at our starting point, the least electronegative atom goes in the center. The more electronegative atoms, they like to stay in the periphery because essentially they can hog the most electron density that way if they are on the outside and they have the maximum number of lone pairs they can have, and they don't have to bond with as many other atoms. All right, so the rest of those electrons, once we've tallied them up and we've made these single bonds to everything, we then can distribute those as lone pairs around those outside atoms. And so then we get the octet around each one of the atoms. All right, if any electrons remain left over, those are going to go in the central atom. And we usually see this when we have one of those exceptions where the central atom is expanding its octet. It has more than 8, it's got 10, or if it's got 12. So we do see that happen. Now, if the atom does not have an octet at this point, then this is where we need to rearrange lone pairs and allow for more sharing so that one of those atoms does get its octet, but it's all due to sharing in just a different way from other atoms. For example, making a double bond to allow more sharing of more electrons to make sure everyone's got their octet. So those exceptions, I mentioned them quickly earlier, but let's take a look here. Okay, so now that said, we have these exceptions. Most molecules are going to follow it. Most atoms are going to follow it. But the ones to watch out for, these are called electron deficient if they've got less than 8, or hypervalent. Hyper means more than or lots of. So lots of valence electrons. And we've got possibilities here in terms of electron deficient. One possibility is that an atom occasionally has 7 electrons. This is really commonly seen for nitrogen. Nitrogen is stable enough that it can exist with just 7. Now, these are called free radicals whenever you have an odd number of electrons. And you essentially are just trying to get that nitrogen as close to 8 as possible, and all you can get is 7. We can't just throw another electron on there. You have to go with the number of electrons that each one of these elements has to begin with. We do give the octet to the oxygen because it is more electronegative. It's going to be better at hogging those electrons. It's going to want those 8 electrons. Another possibility is that there are a couple atoms that are okay with 4 and 6. Beryllium is a lot more rare. I'm seen in these Lewis dot structures because it is more metallic, but it can be okay with 4 electrons. Boron, on the other hand, is fairly commonly seen with 6 electrons. That's not unusual. And then in terms of these hypervalent molecules, this is where the central atom can expand its octet to 10 or 12 electrons. And here's some examples. These are the central atoms that are capable of forming this hypervalent state. And we pretty much just start with phosphorus. And phosphorus, sulfur, chlorine, very common. And then all of those below them, arsenic, selenium, bromine. Now, krypton and xenon, these can be forced to form molecules if they're reacting with fluorine or something very electronegative like that. These aren't going to be super common, but you do see them once in a while with those electronegative atoms. Then we've got antimony, tellurium, and iodine can also expand their octets. Here are a couple examples of what you might see. So here's sulfur. That's got 6 single bonds around it. So if we add up the electrons that are around it, it's got 12. And over here, phosphorus in this molecule, it has these 5 single bonds around, so that means it has expanded its octet to 10. All right, so this is all we're going to talk about in this part 1. And in part 2, we're going to head into looking much more at the geometry and the shapes of these molecules.